넌 거기 앉아 있는 게 어때? 자리 없어. Here, she's from Paris. She'll talk about flow augmentation. Please.
So this is a joint work with Stefan Kratz, Martin Pilipchuk, and Magnus Armstrong. So it's based on 3 papers with the same set of authors. So 2 years ago, about this time, in this series of seminars, I proposed the following future works at the end of some talk. And this very talk is about answering the questions I proposed 2 years ago. Okay, so let me motivate the problem. So we all know about minimum ST cut. So given a directed graph, and every graph I talk about is a multi-graph, so you can have multiple arcs between 2 vertices. And I also give you some positive integer.
비디오가 안 나오고 있다는 유튜브. 퍼블리시 안 한 거 아니야?
퍼블리시는 했는데요.
프라이빗 아니야?
프라이빗이 아니라
프라이빗이야.
프라이빗이었어.
It was a private video.
Yeah, and I give you some positive integer k. And here the problem is to find on ST cuts. So it's a set of edges. So I often call arcs edges. Set of edges. So that between these 2 vertices S and T, there is no directed path after deleting these edges. So I assume you are familiar with the problem. So it's one of the classic problem, and it's polynomial-time solvable with, for example, fourth person algorithm. And now, and like immediate corollary of this max flow min cut algorithm, max flow min cut theorem is Menger theorem. So let's consider some weighted version of this ST min cut problem. So here we are again given the directed graph with integer k, but I also give you the weights. So let's say these are integral weights, and also I give you an additional budget w.
And you also are given S and T, right?
Oh yes, S and T. Yes. And now we want to find an ST cut, and the cardinal. You have 2 constraints. One is that the size of the cut should be most k, and the weight sum of this ST cut is most w. Okay. So it's a natural generalization, natural weighted version of the ST min cut problem.
Is it weights on the vertices?
Weights on the edges.
Okay.
Oh, sorry. Okay. Weights on the edges. Yeah. Well, you can, if you have a vertex weighted version, then you can convert it to edge weighted version.
So when you say G plus, do you
Positive. So yeah.
positive?
Yeah, if it's 0, then you just remove them. Okay, so here is an instance. I borrowed it from one of my co-authors' slide. So you have these 2 vertices, and you have these arcs, and now you have these weights on each edges. So if you think of the minimum weight ST cut, then you will choose probably these 2 edges and these 2 edges. So they have cardinality 4 and weight 4. So if my instance asks whether there is a cardinality M03 ST cut of weight M04, then it's a no instance. You don't have such a thing. but while keeping the size budget at 3, but increase the weight budget a little bit, then it's a yes instance, because you can choose these 3 edges, so the cardinality is small, while you sacrifice the weight a little bit. So this is our problem, and the question is whether, okay, and this problem is NP-hard. So the question is, can you have an FPT algorithm with respect to parameter k? So if you have parameter k and w, then it's easy to, yeah, it's polynomial time. Oh no, it's FPT. But now we want to have an FPT algorithm with respect to one parameter k. Okay, so in a very particular case where you know that the solution you are looking for is actually a minimum cardinality cut, then you can design a polynomial time algorithm in the following way. So let m be some integer which is quite large, prohibitively large. And now I add this constant m to all the edges of the weights. And now we find the ST cut of weight at most k times m plus w. So what does it mean? Now because we added this prohibitively large integer to all the weights, like every one more arc is too costly. So you will naturally confine yourself to search among the minimum cardinality cuts, and among them you find the minimum weighted ST cuts, and that will give you the answer. So it will give you cardinality at most k and minimum weighted ST cut. And this reduction doesn't work when the solution you're looking for is not a minimum cardinality cut. So I'll just call it minimum cut. So whenever I say minimum cut, it's minimum cardinality cut. So yeah, if z is larger than the minimum cardinality cut, then this doesn't work, because once you add all these prohibitively large integers, you will, although z has the minimum weight before you modify the weights, after modifying the weights, every extra edge is too costly, so z will not be an optimal weight cut anymore. So this simple reduction, like a reduction into polynomial time solvable case, works only when the solution is a minimum cut. So it means that this minimum cut assumption is very powerful. So it would be very nice if we can lift the value of, so lambda is the max flow value, like max flow value or min cut value. So if you can lift this value up to the size of the solution you're looking for, then it gives us a very handy way. Like you can, for example, here we modify the weights a little bit and convert it into an efficient case. And you can imagine that for other graph cut problem, if you can make this super powerful assumption, maybe there is a hope to design some FPT algorithm. So that's basically the agenda. And that's exactly what directed flow augmentation technique is doing. Any questions so far? So the flow augmentation theorem, so this is a simple version. I will just stick to this simple version throughout the talk. So it says that there is a polynomial time algorithm which gets as an input a directed graph, multigraph, with 2 vertices s and t and integer k. And the output of the algorithm is a set of vertex pair which you will add as an arc to the current graph. So hopefully this A will lift up the max flow value up to the size of Z. So that's the hope. And so it will output some set of arcs, and for this set of arcs, with a good probability, the following holds. For any minimal ST cut Z of size m most k, Z will become the min ST cut, as we hoped. Okay, so first, Okay, forget about the polynomial time algorithm part, but let's just think about existence of such a set of it's not exactly arc, but set of vertex pairs. So the existence of such vertex pair is easy to see.
But the A is not written anywhere else.
Oh, sorry. ST cut in G plus A.
Ah.
Okay, I omitted the important. Right. Yeah, G plus A. Sorry. So first, the existence of such A. So let's say Z are these. So Z is a minimal cut. So consider arbitrary minimal ST cuts, and there will be some set of vertices reachable from S, and set of vertices which are not reachable from S. Okay. Now I will add arc from S to the endpoints of Z, and I will add the capacity is infinite, meaning that I have k plus 1 multiplicity of these arcs. So if A is like that, and also you add A like this from the head of edges in Z to T. So now this will be really the bottleneck of any ST flow, and that will be the minimum cut. So there exists such set of vertex pairs, but the difficult part is that Z should still be an ST cut. So so hopefully you want to randomly add some arcs between any vertex pairs and hope that you will eventually make this part super dense, this part super dense, so that Z becomes minimum ST cut. But this strategy will fail if you just once accidentally add an arc like this. Right? So the difficult part is really getting polynomial time algorithm with good probability while maintaining Z as an ST cut between them. So and if you add empty arc, then Z will be an ST cut, but it will not become minimum cut. So you need to add enough number of arcs, but still you have to maintain the property that Z is an ST cut. So there is this, these two are contradictory demands. So basically the algorithm, so I'll not give you the algorithm, so we will consider it as a black box algorithm. But this algorithm basically makes a very sophisticated randomized guessing for which kind of vertex pairs needs to be added. Why? So that we don't disturb Z, so we do not add an arc like that accidentally, but we add enough arcs among vertices reachable from S, also vertices not reachable from S, so that they become, Z eventually becomes a minimum ST cut. Yes.
You don't care about the size of A, right? This can
we don't care about size of A.
Okay.
Yeah.
And the set A should be independent of the choice of Z.
Yeah.
Oh.
So
Oh,
yes,
I see.
Z it should be
Oh.
independent of Z. So this example shows that there exists some A, but we want this property for hidden Z. Z will be eventually a solution, and we yes.
Yeah, what happens if you have multiple different minimum cuts?
So then
It's
for
just for one.
some arbitrary choice, the property will hold with this big probability.
It's a small.
Yeah, it's this probability is big for designing FPT algorithm.
I see.
Okay, does it make sense? Okay. So, right. So I will. So this is just rewriting of this previous theorem as a reminder of what black box we are relying on. Okay, so using this flow augmentation technique, given this tool, now let's go back to this bi-objective ST cut. So we have cardinality constraint, but also weight constraint. So what do we do? Let's say k equals 3, so that's our input, and we apply the flow augmentation for this k, and obtain some a vertex pairs. So we add them. So after adding them with high probability, the solution is hidden from us, but it exists. So this solution will become the minimum size SD cut after adding these vertex pairs as arcs. And we use this previous subroutine for finding minimum weight solution. Yeah. Okay. So it's pretty simple, but the problem, so this is a very natural problem, and people asked, and also we will see that this will be the cornerstone of all the graph cut, like many graph cut problems and their weighted version. But it was open, and it was posed as an open question many times. So really the big breakthrough is the flow augmentation thing. So this is a randomized FPT algorithm because of the because the flow augmentation algorithm is randomized, and so it's in our to-do list to de-randomize it. We don't see any major obstacle to de-randomize this algorithm. Okay, so instead of showing how the flow augmentation algorithm is actually implemented, I will show how problems which don't look like cut problems at the surface can be actually cast as a cut problem, and how to apply this flow augmentation technique to obtain FPT algorithm. Okay, so L chain set. So I'm not sure whether you are familiar with constraint satisfaction problem, but probably you heard about two sets problem. So it's some some modification, like some variant of a two-set problem. So the input is a formula, it's a conjunction, like AND of constraints. And each constraint is one of the following form. Either it's a unary clause, so X, or negation of X. So if X is assigned with 1, then this clause will be satisfied. If X is 0, then this clause will not be satisfied. And here it's the opposite. So either it's a unary clause, or the constraint is an AND of following implication clauses. So this is an implication clause x1 implies x2. So in the more traditional form is negation of x1 or x2. So this is equivalent to x1 implies x2. Right? So the first, these two clauses will be satisfied if x1 is 1 and x2 is 1. But if x1 is 1 and x2 equals 0, then it's not satisfied. And when x1 is 0, so x1 is false, then any value is satisfied, satisfying this clause. So so I will call this chain clause. The chain clause will be violated if any one of these implication clause is violated. Okay, so it's rather. And the question is to find the truth assignment, so that you violate MOS K constraints and MOS weight, whose weight sum is MOS W. The weight is on the constraint, so either on the chain constraint or the unary clause.
So when you write that form, that chain form, you can write like negation of xi or whatever.
Yeah,
Okay.
yeah, you can do that. Yeah, but it's called chain because the first clause, the x2 will be the first literal of the next clause, and x3 will appear in the next clause, so on and so forth.
So yes. If I write not x2, then I should say not x2 in the next one?
Yes. Yes.
The length of these chains is always L.
Yeah,
They're
MOS L. So
the same.
yes. Okay, good question. So L is the bound, the bound on the number of implication clauses in a chain set. So so here technically there are L minus 1 implication clauses, but let's say it's L.
Just to double check, like this
Yeah.
xi in the chain clause can be a negation of variable or
No,
They're
they
all
are
positive.
positive variables.
Huh?
Yeah, they are positive variable.
Oh,
So that's why the unary clauses are important. So if
I
you
see.
don't have
So-
any unary clause, then putting true, assigning 1 to every variable will trivially satisfy them. But because of the unary clauses, especially the negation, you cannot do that. At some point you have to violate. So yeah, this will become clear in the next slide. So-
sorry, are you assuming that x1 to the xl are all distinct?
Sorry, could you
Are
say?
you assuming that those x1 to the xl are all distinct?
Yes, they are distinct. No, actually you don't, they don't have to be distinct. No, they are not distinct. It's just it's basically a path.
But you have to use positive form, right?
Yeah, you have to use positive form.
Okay.
Okay, so it looks a little bit weird, like a very particular constraint satisfaction problem, but actually it's one of the cut problems. So you will see how it reduces to a cut problem. It's one of the cut problems where we don't know, even for the unweighted version, we didn't know how to solve, and also it appears as the key missing piece for some important problem. So okay, so let's just put it away. Okay, so how to put it, how can we rephrase it as a cut problem? So let's consider these constraints. So you have some unary clause on x1 up to x4, a negation unary clause on y1 up to y4, and chain constraints where xi implies wi, wi implies yi implies wi plus 1, modulo 4. Okay. Then you can naturally draw it as a directed graph. So S means that S represents a constant true, 1. And T represents constant false. And whenever you have unary variable, like unary clause x1, positive unary clause x1, then you add an arc from S to xi. So it means that if S is a constant 1, but if x4 is not if it's assigned 0, then you want to express that this clause will be violated, and that violation will be represented by a cut by an arc with tail 1 and head 0, and that will represent a cut. Okay, that's the basic idea. So okay, now you can naturally express all the unary clauses and the two clause in the chain set as an arc. So from S to all the positive unary, you have an arc. From yi, which are negated unary clause, you have an arc to T, and for each implication clause, you have an arc. So xi to wi, you have an arc.
So in this form phi,
Mhm.
shouldn't you use or instead of and for this?
Well, it's an and. So you can just write it as you have a you can say that you have a collection of constraints, and you are allowed to violate at most k constraints.
Oh, violating a most key
Yeah.
constraint. I see.
Violating at most k constraints. Okay, so you can express all these two clauses and unary clauses as with an arc, and I want to express that Ci, these chain clauses are bound together, and these are expressed as these colored arcs. So this orange path comes from one constraint, and another colored path comes from another constraint, so on and so forth. So now you can convince yourself that if there is a satisfying, so consider some satisfying assignment for this input, and then there will be some 1-0 arcs in the directed graph. The 1-0 arc should be an ST cut. Why? If it's not an ST cut, so if there is a path from S to T, S is 1, T is 0, so there should be some transition from 1 to 0 at some point, and that is violated. So we should have added it in the thick one, right? And conversely, if you have an ST cut, let's say we have a minimal ST cut, then there will be vertices which are reachable from S, and let's assign 1 for the original CSP instance, and for those which are not reachable from S, we assign 0. Then the violated, the cut arcs exactly correspond to the violated clauses or two implication. Okay, so the subtle part that we didn't cover is that here, like violating multiple two clauses in one chain constraint is violating just one constraint, right? So you have to somehow incorporate this aspect in the ST cut problem. So here comes the bundle cut problem. So what's the bundle cut problem? So it's again finding on ST cut, but now you have some extra part of the input. So you have a collection of B, and each element in B is called bundles. So each bundle, so these bundles are pairwise disjoint H sets, each of them of size at most B. And on each bundle you have some weight, integral weight. So here, and you want to find the minimal ST cut among the edges which are in the bundle, and you want to violate M most K bundles, and the weight sum of the bundle should be M most W. So what does it mean? So here, yeah. So when you recast the L chain set problem as a ST cut problem, now instead of finding arbitrary ST cut, you want to bind the arcs which come from the same constraint as one bundle. So these will become one bundle. The blue path will become another bundle, so on and so forth. So they will be the bundle. So and the SXI arc will be a singleton bundle, and you want to violate M most K bundles, and that corresponds to violating M most K constraints. Yes.
Can I have, say, the implication W1, Y1 in several of these chain constraints?
Implication W1.
Can I have like single occurrences of implications in several chains?
Yes, this is possible, and then you will. So because you want to impose this disjointness, it's only for convenience actually.
Okay.
So yeah, in that case, you just add multiple arcs between these two vertices. Okay, so I hope you're more or less convinced that this L chain set can be formulated as a weighted bundle cut, where each bundle is a directed path of length M most L. And now you want to, instead of solving L chain set is equivalent to solving bundle cut, where each bundle is length M most L path, directed path. Okay, and the problem that we saw at the beginning, the bi-objective ST cut, is a bundle cut problem where each bundle is just a singleton arc. Any questions so far? Okay. So for the bi-objective SD code, each bundle has size exactly 1. For the L chain set, each bundle was a directed path. But if you don't have such a constraint, so for example, in general, if each bundle has size exactly 2, but there is no relation between these two edges inside one bundle, then this problem is W1 hard. So you can simulate a hard problem like a K-click problem. So it's a hard problem in parameterized complexity with the bundle cut problem. You don't even need a weight. Right. But for some particular case of this weighted bundle cut, you can design FPT algorithm. So let's try to, okay. So to emphasize, so it looks a little bit technical, but actually it captures really a wide range of graph cut problem. And we design FPT algorithm for this weighted bundle cut problem with some particular constraint on the bundle. So let's look at another example, how we can cast some problem as an SD cut problem, and especially the bundle cut problem. So here is another very well-known problem in graph algorithm design. Directed feedback vertex problem. So here the input is directed graph with, you have vertex weights, let's assume that they are integers, and you have integer k and w, and want to find the vertex subset. Oh, sorry, I again omitted an important condition. So you want to find a vertex set so that when you remove this vertex set, the graph doesn't have any directed cycle. So you want to delete the most k vertices whose weight sum is most w, so that this vertex set is hitting all the directed cycle. Okay. So even without the weight, this problem was one of the major open problem in parameterized complexity, and it was settled in 2008, which using one of a signature, one of the very important technique called the importance separator technique, and it kind of inspired the entire business for graph cut problems. Yeah. So now it's a natural question. How about the weighted case? Can you solve it in FPT time with respect to k? Okay. Yeah. So it is well known. There is a well-known reduction from the directed feedback vertex set to the following problem. It's called a skew multicut. I will not explain how you do it, but it's quite simple. So what is a skew multicut problem? So you have a directed graph and terminal pairs S1, T1 up to SB, TB, and you have an edge weight, and you have integers, and you want to find a set of edges so that you want to hit skewed directed path. Skewed meaning that from S4 you want to remove all the directed paths to T4 up to T1. From S3 you want to hit all the directed paths to T3 up to T1, but you can have a directed path from S3 to T4. So like upward path is allowed, but like downward path is allowed. So you want to delete edges in this way. So it almost looks like some cut problem, but it's not an ST cut problem. So let's make it into an ST cut problem. So how do you do it? So this is the same copy, B copies. So if you have 4 terminal pairs, then we have 4 copies of the input instance of the skew multicut problem. And I will add some vertex S, vertex T, and from S to S4, so in this copy, you add an undeletable arc to S4. Also, undeletable arc to S3. undeletable arc to S2 in this instance, one is first, and to T there is undeletable arc from T1 in this instance, and in the next instance from T2 to that. But actually I should have and you add an undeletable arc for the copies of the same vertex. So if V is a vertex in the original graph, then for all the copies in G4 up to G1, I add an arc, undeletable arc. So this arc has an effect that there is also undeletable arc from S to S4 here, because there is undeletable arc from S4 to the S4 on this copy to S4 on this copy. So actually I should have put red here, put red on these and these two vertices, so on and so forth. But you can imagine that this is red and these two vertices are red, these three vertices are red, and these four vertices are red, and also the opposite direction. Okay. Then what's the, so now I want to have, so okay, then what does the ST cut in this graph do? So you want to hit all the directed paths between S and T. So if you look at one copy here, these S4 and S3, they are bind to S, so they are red. Also T3, T2, T1, they are also blue, right? Because T2 is connected to T2 with undeletable arc, and T2 is connected to T here, so on and so forth. So in each copy, an ST cut will delete any arc from S4, S3 to T3, T2, T1. And also in this instance, you are going to delete all. You are going to hit all the directed paths from S4 to T4, T3, T2, T1, so on and so forth. So that enforces the skew, the demand for hitting the skew terminals. And in order to make it, okay, and also we don't want to delete different arcs in different copies, so we make them into a bundle. So especially if you have the copy of the same arc, we'll put in the same bundle, and you have these arcs. So in the end, the skew so what we did is recasting the skew multicut as a bundle cut problem, where each bundle, so this will be one bundle, so the copies of the same arcs are one bundle. So the number of edges inside one bundle is M of B, and between any two edges inside a bundle, between these two, there is an undeletable arc between them, because we added this arc, undeletable arc. Yeah.
Can you draw some pictures of that? I try to find.
Right. Sure.
Do all those arcs that you just explained by words.
Right. T2. So here you have T, you have T1, and you have this arc. I will just look at this G2 copy. And you have S. S4, S3, S2. So you have this arc. And these are undeletable edges. So they have
Meaning the weight is high.
yeah, the weight is high. And so, and you want to find an ST cut, and in order to, because these edges will be always available, you don't delete these edges, and they are connected to S. These are connected to T. So you have to delete any connection between S4 to T to T1, S3 to T to T1, S2 to T to T1. So it's kind of like delegate it's a so this copy is a delegation of this skew symmetric demand for hitting the directed path from S2 and higher sources to T2 and lower vertices. So that's such cut. So you will find you will delete some edges here, and also you want to delete exactly the same edges in other copies too. But they will also handle the other demands. So here you will have T3, T2, T1, which are connected to T with undeletable arcs, and S3, S4, they are connected by undeletable arcs. So also in order to be an ST cut, you need to delete all the paths from S4 to T3, T2, T1, S3 to T3, T2, T1, so on and so forth.
So when you make copies, do you always make this, like if you have n vertices, then you have n copies, or
Oh.
2 to n copies, or?
So the number of copies is the same as the number of terminal pairs. So you have B terminal pairs, then you have B copies. Yeah. So the bundle size is at most B.
Why we need delete same copies in the same? Why we need to delete same vertices in the second method?
Oh, because by this bundle cut problem, you want to simulate the skew multi-cut problem. So whenever you have some ST cut, you want to retrieve the ST cut in the original instance. Right. So easiest way is to forcing like having the same edge set in all the copies. Or yeah.
Okay, maybe I realize that skew multi. Can you show the definition of skew
Oh,
multi-cut
yeah.
again? Maybe that's the reason why I was a bit struggling.
Yeah, but well, yeah, well, I think it's like understanding
Yeah,
like
okay.
this particular reduction is not super important.
Right.
Yeah. Okay, so the skew multiple, yeah. So you have the terminal pair S1 T1 up to SB TB.
Uh-huh.
So actually the parameter here will be B and K. So we are going to have a FPT algorithm with respect to B and K. And you want to find an edge set so that when you delete them, there's no directed path from Sj to Ti, where J is at least as large as Ti. So
Okay.
from S4, you don't want to have any directed path to all the terminal. From S3, T3, you don't have directed path from T3 up to T1. So on and so
Alright.
forth. Right. Okay. So anyway, I think the main message here. So if the reduction is not very persuasive, then
Now reduction is good.
okay, right. Yeah. So the main message is actually the following: the skew multiple. So the directed feedback vortex that can be reduced to the skew multiple problem. A skew multiple problem can be recast as a ST cut problem, and especially bundle cut problem, where each bundle has size at most B, and between any two edges in a bundle, there is a directed path, undeletable directed path. So this existence of this undeletable directed path gives us a hope for designing FPT algorithm. So if you don't have it, then it's you can have W1 hardness. Okay, so you can see that this bundle cut. So this second condition already holds for L chain set, because L chain set in the L chain set, like each bundle is just a directed path. So between any two paths, there is a trivial undeletable path. Okay. Okay. Yeah, almost. So yeah, so like one of the tractable results in our result is algorithm for algorithm that works for L-chain set, also for this bundle cut with some specific constraints and much bigger generalization of it. But let's see it just for L-chain set problem. So L-chain set is the this problem, and how does it work? So first, we invoke the flow-augmentation algorithm. So we want to find the minimal ST cut whose edge set is contained in at most k bundles. And the weight sum of these bundles are at most W. So that's the minimal ST cut we want to find. Okay, so the algorithm works as following. So first we invoke the flow augmentation so that Z becomes a minimum ST cut after adding some arcs. And the important observation is that Z is contained in at most k bundles, and each bundle contains at most b arcs. So, and Z is a mean cut, so the mean cut size is at most bk. And these P1 up to P7, they represent some max flow. So you can consider, so the max flow can be understood as edge disjoint path between S and T, right? So instead of edge disjoint, I just assume that they are vertex disjoint. Yeah, but just to simplify the argument. So let's say these are the edge flow paths. We call them as flow paths. And Z is an ST mean cut, so Z should contain exactly one edge in each of these flow paths. Okay, so after obtaining the flow path, now we guess how the violated bundles are lying on this flow path. So for example, so we have this 7 flow paths, and there will be, suppose that we are looking for solution violating almost 3 bundles. So now we guess something like, oh, these 3 paths, the violated arcs on these flow paths should be contained in the first bundle, bundle 1. The violated arc in the second flow path should also contained in the bundle 1. And also these arcs should also be contained in the bundle 1. And the 2 violated arcs in the 4th and the 5th max flow should be contained in the same bundle, so that's bundle 2, so on as first. So because they are at most bk flow paths, and we are the number of bundles is at most k, there are like only f of b comma k different possibilities for this guessing.
So violating a bundle now just means contained in Z?
Yeah, yes. Z contains some arc in the bundle. Okay, so let's fix one guess, like how the one violated bundle looks like, and the second violated bundle look like, and third violated bundle look like. And now we look at all the bundles which really conform to this form. Where the first edge lies here, second edge doesn't lie on any path, the third edge lies on the second flow path, so on as first. So you can like filter out bundles which do not satisfy any of these gets to form. So these are the bundles. So these are the bundles which conform to the guessed solution type. And the key observation is the following. So if you have two bundles, one where the one takes a path like this and another takes a path like that, then is it possible that this bundle is violated? Suppose this bundle is violated. It means that the ST code will contain this arc, and also this arc. But then this arc will connect on S a vertex which is reachable from S, and the vertex which is that connected to T. Because you can violate only one of these three bundles. So whenever you have such a crossing between two bundles of the same type, you can get rid of the one which is crossed by the other. So, okay, after fit. Oh, actually I should have deleted this and kept this one. Okay. Anyway, so after filtering out some unavailable bundles, all the remaining still viable candidate bundles should be linearly ordered. There is no crossing. So now because of the linear ordering, I'll not give you the detail, but you can somehow see that you can compress the bundles and obtain some minimum ST cut instance weighted. So each of these colored arc represents the bundles. So the weight of this arc will be inherited from the bundle that it comes from. So now it becomes a really arc weighted minimum ST cut problem, and which we know is a polynomial-time topic. Okay, so I will try to wrap up the talk. So this is not exhaustive list of unweighted cut problems. There are many cut problems. We also saw that some problems which don't look like cut problems on the surface, they can be recast as a cut problem. And there is a series of very nice techniques for solving these problems. So there's also these algorithms. And but there were some cases where even the unweighted cut problems was open, whether they are FPT or not was open. Notably this L-chain step problem, and there is another problem called directed multicut for terminal pairs and most 3. I will not define the problem. And what the flow augmentation technique enabled, it resolved this open case for the unweighted problem, but even for the weighted problem, we can solve this L-chain set not only for the unweighted but also for the weighted. So we saw that this directly feedback vertex set can be reduced to some weird bundle cut problem, and this is this blue box is an even bigger generalization of this bundle cut problem. And some other problems can be also reduced to this special case of the bundle cut problem. And and it's crucially relies on the flow augmentation. So one remark I want to make is so for the directed multicut problem, unweighted directed multicut problem, it is known that when you have 4 terminal pairs, it's hard, it's intractable in parameterized complexity. And when the terminal pairs is MO3, then it's FPT. And this FPT algorithm doesn't use this algorithm for this blue problem, but it uses a flow augmentation, and also it uses some twin width argument. It's very interesting. So did I put some open problem? No, I didn't put open problem. Okay, so this is it. Thank you for attention.
Right. Thank you. Any questions?
So when you explain flow augmentations, I mean, initially I thought the setting is about this mean cut, but then later when you talk about this bundle,
Yeah.
it's about like a cutting bundles instead of cutting edges.
So when I said violating a bundle, it means that the cut contains an arc from the bundle.
Right, right. But then you want to be sure that the number of the minimum cut in that sense is measured in terms of how many bundles you remove.
Oh yeah, so the bundle cut problem has two parameters. One is the number of violated bundles and the size of the bundle, like how many arcs you have in the bundle. And the FPT algorithm.
So what worries me was like after the flow augmentation, the
Yeah.
standard graph.
Yeah.
Suppose the minimum cut happens to have cut 5 edges,
Yeah.
but suppose 2 of them belong to the same bundle.
Yeah. So in the case we do the flow augmentation with respect to 5. That's why it's important to have the bundle size bounded, because if the SD cut violates k bundles, but there is some bundle of infinite size, then you have to invoke the flow augmentation with respect to arbitrarily large k. And that's not really feasible for a FPT algorithm.
Can you give us some intuition behind the flow augmentation? I mean, randomly you have to pick like two vertices in
Yeah.
kind of same block, right?
Yeah. So, okay, that's a very good question. So, so
Like I was imagining that maybe that you pick one vertex and go like 2 step and just add an edge or something like
so
that.
yeah, it's much more sophisticated than this. So we basically, I'm not sure whether I remember it correctly.
Uh-huh.
I have to recall. So
Should I start
we
the
look
recording?
at, so the minimum cut size is almost k. So let's say we start with some minimum cut size is lambda. So let's start with some flow paths, lambda flow path. So basically we first to look at the blocks. We group the vertices into blocks so that within each block the connection between each of these lambda flow path is the same. So here, okay, so what I mean is that let's say this is these are the flow paths. So we first try to decompose the flow paths into consecutive blocks, so that within each block, if you have a connection from the first flow path to the second one, second to the first one, and then you have the repetition of the same type. So the connection type between the flow paths is the identical. So if you can have that many blocks, then it means that our solution size is bounded with respect to lambda, is bounded by k. So you cannot really, so the blocks which are affected by z, so z is taking some edges like that. So there are not too many blocks.
Uh-huh.
So if the number of blocks is too many, then if you make random guessing, by guessing that maybe z won't be inside this block, then this your guess is likely to be correct if there are too many blocks like that.
Uh-huh.
Yeah, and then you try to add some arcs like this. If there are few blocks, then you do some kind of branching step. And actually, there are a lot of subtleties that I don't remember, but it's basically like you do that kind of guessing.
Uh-huh.
Yeah.
I see. So you decompose graph into
Yeah.
by the minimum order
Yeah.
cut.
Yeah, and then when you cannot do it, then you try to add some arcs so that you increase the connectivity between the flow paths, and the number of flow paths is bounded, so you cannot increase the connectivity types between the flow paths arbitrarily high. Yeah.
I see. Other questions? Okay, if not, let's thank you.